Hi guys, this is Dr. Gonzalez here, and I have put together a presentation with a few extra examples of ANOVA. I mainly did this because in the past I've had a lot of people ask for extra examples, so this presentation I'll walk you through two more, and there are data sets that you can download in Canvas. You'll need the one-way ANOVA for anxiety and the two-way ANOVA PSYC. And those are both in the same place where you found this video. So I'm going to be walking you through that, and I'll have Jamovi open as well as we go through it. So for the first one, the one-way ANOVA, or this is a between subjects ANOVA, we have this research question. Does type of anxiety medication affect anxiety symptoms severity in adults? So this is kind of a typical setup where we're examining three different medications and how they affect a person's anxiety. We have sertraline, which is Zoloft, alprazolam, which is Xanax, and then a placebo medication. And we're measuring anxiety using the GAD-7, which is scored from 0 to 21, and anything that is a 10 or above would indicate generalized anxiety disorder. And the analysis we're going to run is a one-way between subjects ANOVA. So that means we have one factor, which is medication type, and we've got three groups, group 1, group 2, and group 3. And that also means that each participant is only assigned to one particular condition. So each participant only gets one medication. Our null hypothesis, remember there are two ways that we can write this. We can write it using words or we can write it using mathematical notation. The first one simply says for our null, there's no difference in mean GAD-7 scores among adults assigned to sertraline, alprazolam, or placebo. And the mathematical way of writing that is that the mean of sertraline is equal to the mean of alprazolam, which is equal to the mean of the placebo. And then our alternative says that at least one medication group has a different mean GAD-7 score. And we write that simply by saying that not all mu values are equal. So we have our number of groups, which is K, equal to 3. Means you've got group 1, group 2, and group 3. Our total sample size was N is equal to 33, which means we had 11 participants per group. And so we have 2 degrees of freedom. We have our between groups and our within groups. We calculate our between groups by taking the number of groups, K, and subtracting 1. So K minus 1 gives us our degrees of freedom between of 2. And our degrees of freedom within groups would be the N number, N minus K. Degrees of freedom within would be 33 minus 3, which gives us 30. So when you report your ANOVA results, you report it as F of degrees of freedom 2, 30. So if you pulled up the F table, you would need to find your critical value. You're going to use your numerator and denominator degrees of freedom. So our numerator degrees of freedom is going to be the top number right here. We had calculated that to be 2. And your denominator degrees of freedom was 30. So that goes down the side and you find the intersection of those two numbers. So 2 and 30 gives us a critical value of 3.32. And that is going to be corresponded to a p-value of 0.05. Now remember, in Jamovi, you aren't going to have to find this critical value. What we do in Jamovi is simply look at our p-value and interpret from there. So now you're going to need to find your your data set. So open up Jamovi, okay, and then go to Open and Browse and find wherever you saved your download. On my computer here, I believe I saved it in my ANOVA file, and we're looking for one-way anxiety. So what you get should look like this, and you can assure yourself that you're in the right place by looking at the treatment variable. You should see placebo, sertraline, and alprazolam. And then our other variable that we had was GAD-7. Okay, let me move this out of the way for you. Now we're going to go to analyses, ANOVA, and one-way ANOVA. So over here, you go to analyses, ANOVA, one-way ANOVA, and you're going to have your ANOVA menu right there. Okay, let's go to the next slide over here. You're going to move your appropriate variables over. Our dependent variable is going to be the GAD7, so you're going to move that to dependent variable, and your grouping variable is the treatment group. So let's show you how you do that over here. So our treatment group was our grouping variable, and the GAD7 was our dependent variable. Now, if you notice, if you just do that, the only thing you get is output for an ANOVA. You don't get any of the associated information that we need to be able to make any sort of determinations. So let's walk through what else you're going to need to select. So we want to assume that we have equal variance, okay? If you don't assume, it's going to run a different ANOVA and your answers are going to be incorrect, so make sure that you assume equal variances. You're going to need under do nothing for missing values because there are no missing values in this particular data set. Under additional statistics, you need to make sure you click descriptives table because you need that in order to be able to get your descriptives for the output. Under assumption checks, you would make sure that you click homogeneity test. And then under post hoc, we need to be able to see where our differences were between the different groups. We want to select Tukey because that is used when we have equal variances. And then under statistics, make sure you've got mean difference. You can also click report significance, and that'll just flag the ones that are significant. You also want your test results, which is the T in degrees of freedom, and to flag significant comparisons. So let's go over here and make sure those are all clicked. So for variances, don't assume. We want to make sure we do assume. So unclick under don't, okay? Don't do anything for missing values or don't change anything. Under additional statistics, you want your descriptives table. Under assumption, we want to check for homogeneity. And you see every time you click something, it adds something to your output, and that's important, right? Under post hoc, we're going with Tukey because we assumed equal variances, and that is the correct assumption, and I'll tell you why in a minute. And then we want mean differences, report significance, our test results, and flag significant comparisons. So now you've got this output here that we're going to need to interpret. Okay. Right. Let's go to the next slide here. First thing we're going to do is we're going to look at Levine's because Levine's is going to tell us about our homogeneity of variance. So if you look for Levine's under assumption check, we've got an F value that is extremely large in number of numbers, so they had to use scientific notation. That doesn't really tell us much, but the p-value does. So remember for homogeneity of variance, if it was significant, that would mean that we had an issue with homogeneity of variance. So in this particular test, we're looking for a result that is not significant, and that's exactly what we found. Our p-value is equal to 1. So that tells us we did not violate the assumption that the variances were equal. That is what we want because that means we can proceed with the test that we have selected. And there's where I told you what I just said. So our p was 1, it's not significant, so then we can proceed. So go to the next slide. Then you're going to evaluate your ANOVA results. Our results were from the top table for one-way ANOVA. We had a critical value that we established earlier of 3.32. And our value that we got was 99.4. 99.4 is obviously much larger than 3.32, so we reject our null. That means that somewhere in here there is a significant difference between those treatment conditions. And because this is Jamovi, and Jamovi doesn't operate by critical values, it operates using the p-value. If you looked at your p-value, you would get p is less than 0.001 right there. And there's our f. There's degrees of freedom 1, degrees of freedom 2. So f of 2 and 30 is 99.4, which is less than 0.001. And if you look in your results, I'll show your output. I'll show you exactly where that came from. That comes from right there. One-way ANOVA Fishers. Okay. Now underneath that, you've got your group descriptives, and that's what we will need later on when we go to talk about where the difference was and what the mean was. Because remember, we're talking about an outcome, which was a score on the GAD-7, and somewhere between those three groups, one of those three groups is significantly different from the other two. So let's move on here. So remember, omnibus, ANOVA is an omnibus test that just tells us that at least one group is different. It doesn't tell us which mean is the different one, so we have to do those post hoc tests. So we ran Tukey's, and there were 3 pairwise comparisons in there, and those were flagged as significant in 2 of those occasions. So if you look at post hoc tests, this is where you're pulling those results. It's comparing alprazolam to the placebo, alprazolam to sertraline, placebo to sertraline, placebo. You can make those comparisons right there. The last one you don't have to worry anything about because that's just comparing sertraline to sertraline. So where is that coming from? That's coming from your output all the way down at the bottom. Post hoc test, Tukey's post hoc. Alprazolam compared to placebo was marked as significant. Alprazolam and sertraline was marked as significant, and then placebo to sertraline. So what that means is that alprazolam and sertraline, alprazolam was better than sertraline, alprazolam was better than placebo. Placebo was not better than either of the other two. And by better, I mean it produced a lower GAD-7 score. So this is what I just told you right there. You've got your mean differences. You'll need those for your write-up. Then you have your t-value. That's your Tukey's value right there. You have your degrees of freedom for your Tukey's test. And then you have your p-value for that comparison as well. So how do you interpret that? Go to your results that we just looked at, and alprazolam versus placebo had a mean difference of negative 7.82. P is less than 0.001. So what that means is that in the group that received Xanax, they had GAD-7 scores that were about 7.82 points lower than the placebo group. That's that mean difference. You got that right here from mean difference, alprazolam and placebo. And you're probably also wondering, well, how did you know which was which? Well, if you go up here to your group descriptives, this is where you get your mean for each group. So the mean for alprazolam was 7.09. The mean for placebo was 14.9. The mean for sertraline was 10.91. So if I'm comparing alprazolam to placebo, the difference between those two is reported down here, 7.82, the mean difference between placebo and alprazolam. So you kind of have to look at both your post hoc test chart and your group descriptives to see which one is which and to orient yourself to know what the original means were for each group so that you're saying, well, what is this mean difference? This mean difference right here is between alprazolam and placebo. Which one was which? There's where you can tell which one was which. You can go back up to this group descriptives and see that placebo had a mean of almost 15 and alprazolam had a mean of around 7. So if you subtract those, you get your difference right there. All right, if you looked at the alprazolam and sertraline, had a mean difference of 3.82. P is less than 0.001. That was also marked as significant. So that means that the alprazolam group had GAD-7 scores that were about 3.82 points lower than the sertraline group. And you can look back at your results, and you can see sertraline was 10.91. Your placebo is 14.91. Your alprazolam is 7.09. So if you look at the difference between alprazolam and sertraline, it was 3.82, which means alprazolam worked best, then sertraline, then your placebo. That gives you your third comparison down here, which is sertraline to placebo, mean difference of 4. So that means that the placebo group had GAD-7 scores that were 4 points higher than the sertraline group. You'll notice these were negatives, and this is a positive right here. So that's what I mean by orienting yourself by looking at the mean difference and then going back up and looking at the means for each group. So sertraline and placebo, there's where you can see 10.91 and 14.91. Placebo had scores that were about 4 points higher than sertraline. So how do we write all of this up? It's going to be pretty long. It's going to have 3 parts. You're going to need to report Levine's, then your omnibus ANOVA, and then your post hoc tests. So the first thing you would do in a statistics write-up is write up your results for Levine's, and you would say that the Levine's test was not significant, and that indicated that we had homogeneity variance. We did not violate that assumption. And you report that by saying F of 2 and 30 is equal to 0. It was actually different. If you look right here, it should have been right there. Somehow that number got converted, but that's the number that should be in these results right here. But our P was 1, so we went ahead and conducted our one-way ANOVA. And we are conducting that ANOVA on GAD-7 scores by treatment group. We list out our 3 treatment groups. And then we report our omnibus ANOVA results. We say the results showed a significant effect of treatment group on GAD-7 scores. And you report that general omnibus ANOVA, which came from right there. Our F is 99.4 with degrees of freedom of 2 and 30. And your p-value is less than 0.001. So that's the first part of the write-up. The next part of the write-up, you're going to go into the mean differences, and you're going to report your post hoc, the Tukey's, to show where those differences occurred. So group descriptive showed that participants in the placebo group had the highest anxiety scores. Then you report those scores using mean and standard deviation. So in the placebo group, the mean was 14.91 with a standard deviation of 1.3. Then you follow that by the next group and then the final group. So the sertraline group was next with a mean of 10.91 and a standard deviation of 1.3. And your participants in the alprazolam or Xanax group had the lowest anxiety scores. M is 7.09, standard deviation of 1.30. So if you notice, the standard deviation for each one of these groups was 1.3. So that makes sense since our Levine's test right here said that there was no significant difference between the standard deviations. Now, by significant difference, normally there is a difference, right? But because these are artificial data that are made up, they are exactly on the money being equal with regard to that standard deviation. Each group has a standard deviation of 1.3. So our Tukey post hoc tests indicated that all 3 groups differed significantly from each other, with P is less than 0.001. Specifically, we want to report that the alprazolam group was significantly lower than both the placebo group and the sertraline group. And the sertraline group had significantly lower GAD-7 scores than the placebo group. And all of that is coming from Tukey's post hoc right here. Okay. So pretty easy, right? You've got this. So your mean differences, go ahead and you can write about those, and you can clarify those pattern of results by talking about the mean differences between each group. We said that the alprazolam group scored on average 7.82 points lower on the GAD-7 than participants in the placebo group, indicating substantially lower anxiety symptoms. In the alprazolam condition, participants in the sertraline group scored on average 4 points lower than the participants in the placebo group, indicating that sertraline was also associated with lower anxiety symptoms. And then finally, the group of alprazolam scored on average 3.82 points lower than the sertraline, suggesting that alprazolam showed a stronger reduction in anxiety scores than sertraline. So all of that comes from that Tukey's post hoc table. This is where you get your specifics about each group and what each group is doing when it comes to the means and the mean differences that the Tukeys use to make those comparisons. All right, let's go over an example of a two-way ANOVA. Let me close this out right here so we can be ready to go with that. You'll need to get your second data set for this. So go and find the PSYC data set and have that handy. In this particular question, we're talking about how does sleep chronotype and caffeine affect sleep quality in adults. So we have two independent variables. We have sleep chronotype, morning and evening type, and then we have independent variable of caffeine intake. You can either have low intake or high intake. And we're looking at the dependent variable of sleep quality, and we're measuring that using the PSYC. So this is a 2x2 between subjects ANOVA. It's going to have 4 groups. You're going to have morning chronotype with low caffeine, and then morning chronotype with high caffeine. Then you're going to have evening chronotype with low caffeine, and evening chronotype with high caffeine. So there are 4 groups. And we're looking at 2 main effects, and we're looking at 1 interaction. So the main effect of chronotype, we want to know if morning types and evening types differ in their sleep quality. Then we want to look at caffeine. Do people with low versus high caffeine intake differ in sleep quality? And then we also have an interaction effect that we're looking at. Does the effect of caffeine intake on sleep quality depend on whether or not someone is morning or evening chronotype? So whenever we've got a 2-way ANOVA set up like this, you're actually going to have 3 sets of hypotheses. You're going to have 1 for the sleep chronotype, you're going to have 1 for the caffeine intake, and then you're going to have 1 for your possible interaction effect. So for our sleep chronotype, we're going to have a null hypothesis saying that there's no difference in mean PSYC scores between morning and evening chronotypes. And if I write that in mathematical terms, it just means mean of morning is not equal to mean of evening. So your alternative for that is that there is a difference in PSYC scores between morning types and evening types. And mathematically speaking, that just simply says mu morning is not equal to mu evening. We also have a set of hypotheses for caffeine intake. So your null hypothesis, there's no difference in mean PSYC scores for adults with low versus high caffeine intake. And mathematically speaking, we write that as mu of low caffeine is equal to mu of high caffeine. Your alternative hypothesis here is that there is a difference in mean PSYC scores between adults with low and high caffeine intake, and mathematically that's written as mu of low caffeine is not equal to mu of high caffeine. And then we have a set of hypotheses for our interaction. So our null hypothesis simply states there's no interaction between chronotype and caffeine intake, and your alternative is that there is an interaction. So we are not going to look up all of those F distributions in the F table. I mean, yes, all of those F values in that F table. It's a lot of work for something that we can go with Jamovi. Okay, Jamovi is going to tell you your p-values, so there's really no need to go look up all of those values for this particular problem. But you do need to know your degrees of freedom. You've got a 2x2 between subjects ANOVA with 4 groups, and we're going to have 25 participants in each group. So that would be an N of 100. But your chronotype degrees of freedom, number of chronotype levels, we had 2. So 2 minus 1 gives us a degree of freedom of 1. For your caffeine levels, you had 2 levels. You either had low or high. So our degrees of freedom for caffeine would be 1. And we're only going to have 1 interaction. So our degrees of freedom for that is 1. And you would need to know your within groups degrees of freedom, and that is calculated by looking at your total N minus the number of cells. We had 4, so 100 minus 4 gives us a degrees of freedom of 96. So for each ANOVA that you're testing, your F and your degrees of freedom are going to be written like this: F of degrees of freedom 1, 96. And our alpha is going to be 0.05, and if you went to Google or ChatGPT and asked it what your critical value was for this particular setup, or you pulled out that F distribution table and looked it up, you would find your F crit to be 3.94. We're not going to worry about that because we're going to go based off of our alpha level. So we're going to make a decision for each group of hypotheses separately. So if your F for chronotype is greater than 3.94, we reject our null, and that will be flagged in Jamovi based on the p-value. If your caffeine F is less than 3.94, we reject the null for the caffeine hypothesis. And then if our interaction F, chronotype times caffeine, is greater than 3.94, we reject that null. So we have 3 possible groups of decisions that we can make here. So let's see how you would run this in Jamovi. So you're going to go to Analyses and go to ANOVA. So you're going to see one-way ANOVA, repeated measures, ANCOVA, and MANCOVA. And what we want is our ANOVA. So go to the hamburger, go open, find where you saved that file, 2-way ANOVA PSYC. It should look like this. You should have a column for your sleep chronotype, a column for your caffeine intake, and a column for the PSYC total. Go to Analyses, ANOVA, ANOVA. Okay. Next, we're going to move our variables over. Your PSYC is your dependent variable, and your sleep chronotype and caffeine intake are going to be fixed factors. So you're going to move sleep chronotype to, PSYC to dependent variable, and then sleep chronotype and caffeine intake to your fixed variables. And then under your model, you want a model that shows sleep chronotype, caffeine intake, and sleep chronotype times caffeine intake. So down here under model, it should have it set up for you, and it should pull over, and it should look just like this. If it doesn't, you'll have to move something over. There's nothing else to move over here because those are the only variables in there, so everything looks good for that. So let's talk about the other things you need to make sure that are checked. Go to the assumption checks, and first of all, you need to check this right here. You need to check model fit. You want overall model test. Okay. Then under assumption, click homogeneity. Okay. So we're assuming homogeneity variance. Then we need our post hoc test. So under post hoc, make sure that you're clicking on Toogies, and that you want a post hoc test for sleep chronotype, caffeine intake, and that interaction. So under post hoc, we want sleep chronotype, we want caffeine intake, and we want that interaction. Okay. And then you want your estimated marginal means to make sure you've got term 1, term 2, and term 3 both. To move both of the terms for term 3, you've got to select them both and hit the arrow at the same time. So estimated marginal means. So you want sleep chronotype for 1. Then add new term. You want caffeine intake for term 2. And then here you want to take both of these at the same time. So select shift. So click on it with your mouse, then hit the shift button, and then hit caffeine intake, and then put them right there. That gives you that interaction term there. Let's see what else you need to put in there. Nope, that should give you everything. So first thing we're going to do, as we always do, is to start with the Levine's test and to check to make sure we have homogeneity of variance. So you're looking at that output right there. And as we did with our other example, you'll notice that there is a p-value of 1.00, which is telling me that the standard deviation in all 3 terms is the same, because this is an artificial database. But the important thing here is that we have not violated that assumption of homogeneity of variance, so we can continue forward with these analyses. Okay. So next we're going to look at our ANOVA table, and you're interpreting 3 things. We're looking at, does chronotype affect PSYC score? Does caffeine intake affect PSYC score? And then is there an interaction between chronotype and caffeine with regard to PSYC scores? So here's your output for that. That comes straight from Jamovi's output right here. Okay. You'll notice that our overall model is significant. Our p-value is less than 0.001, and your F was 527.5. So our overall model is significant. Sleep chronotype was marked as significant. Caffeine intake was marked as significant. And the interaction came out as significant. So same thing we just looked at from the direct output. Let's interpret that, and how would you write it up? So for the first factor, we had sleep chronotype. We determined that it was significant. So to write that up, we would say F of 1 and 96 was 907.5. P is less than 0.001. So for sleep chronotype, we reject the null. That means that our PSYC scores differed significantly if the person was morning or evening chronotype. So there was a significant difference when looking at chronotype. We would do the same thing for caffeine intake. And our F was F of 1 and 96 is 607.5. P is less than 0.001. We reject the null for caffeine intake. And that means your PSYC scores were different at a significant level for low and high caffeine groups. And then we look at interaction, sleep chronotype, and caffeine intake. We also reject the null for that, because 67.5, which was our F for 1 and 96 degrees of freedom, was significant with a p-value of less than 0.001. And that means that the effect of caffeine on PSYC scores actually depended on sleep chronotype. So in other words, what that's telling us is caffeine intake was not associated with sleep quality in exactly the same way if a person was morning or evening chronotype. So there's an interaction between those 2 variables. How do we interpret those results? Well, we write it up saying that, I didn't write the Levines up here. I think you guys have gotten pretty good at writing Levines, but I skipped straight into the two-way ANOVA results. I said the two-way ANOVA showed a significant main effect for sleep chronotype, and then I reported the statistic, and then I explained it. I said that indicated that PSYC scores were different based on morning and evening chronotypes. And then I also said there was a significant main effect for caffeine, telling me that PSYC scores were different based on whether the person was low or high caffeine group. Then I also reported that sleep chronotype caffeine interaction significant, telling me that caffeine's effect on sleep quality was dependent on sleep chronotype. Now, your post-hoc tests look a little bit different here as well. So, because we had that interaction that was significant, that is the most important one out of this table to look at. So, if you look at your post-hoc comparisons, you had your different groups. You have sleep chronotype, and then you have high caffeine. You have all of those different comparisons here, and they're all marked as being significant with our Tukey's test. So what does this boil down to? It boils down to higher PSYC scores mean that the person has worse sleep quality. A positive mean difference means the first group listed had higher or worse PSYC scores than the comparison group. So we were looking at evening with high caffeine versus evening with low caffeine. The mean difference was 6. That means evening types with high caffeine intake had PSYC scores that were 6 points higher than evening types with low caffeine intake. And that means that high caffeine was associated with much worse sleep quality in the evening types. And that makes sense. If you're, an evening person, you're drinking more caffeine to stay awake, then your PSYC score is going to indicate that you had worse quality sleep. Then we move into our other comparison here, morning chronotype with a high caffeine assumption versus morning chronotype with low caffeine. The mean difference was 3. That was significant. So that just means that morning types that consumed high amounts of caffeine had PSYC scores that were 3 points higher when compared to low caffeine. So let's write that up. You would start with your Levines. You would say Levine's test was not significant. There was no violation. Homogeneity of variance was met. So that meant we went ahead and conducted a two-way ANOVA to look at the effects of sleep chronotype and caffeine on sleep quality using the PSYC. And we also put a blurb here that says higher PSYC scores mean poorer quality sleep. We report the main effects. We said that there was a main effect for sleep chronotype. We reported our F for that statistic. And we also explained it. Overall, evening types had significantly higher PSYC scores than morning types, indicating that the evening chronotype reported worse quality sleep. We also had a significant main effect for caffeine. So that means that if they were in the high caffeine group, overall that group had a higher mean PSYC score, indicating that they had poorer sleep. And then we write up the interaction. We said the sleep chronotype versus caffeine intake was also significant. We report that F value and the significance, and that indicates that the effect of caffeine intake on sleep quality depended on the sleep chronotype, and our post-hoc comparison showed that high caffeine intake was associated with significantly higher PSYC scores for both chronotype groups. Among the evening types, high caffeine group, remember, they scored 6 points higher than the low caffeine group. Among the morning types, the high caffeine group scored 3 points higher than low caffeine. So caffeine was associated with poor sleep quality in both groups, but what did we notice? The effect was stronger on people who reported being an evening type. So that was just a walkthrough of 2 additional examples. If you have any questions, please let me know. A note about your assignments. Your assignments are not going to include super complicated situations. So don't look at these and be frightened. It'll be a straightforward example. And there's a video to walk you through the assignment as well. So reach out if you have any questions or concerns, and take care.